They're all professors. They all teach the. It's just one that actually gets the title.
Got this side. How much
So, good morning everyone, and welcome to lecture number 16, titled as the properties of wood, and the second lecture for the wood series that we have. So, can you hear me well? Back? That's perfect. So, in this lecture, we will be covering multiple topics or multiple ideas behind the wood properties and how we integrate those properties into more applicable applications and more tangible applications, and how the wood properties are affected by the grain direction, and how we test wood, what is the wood production, and what are the wood products, and finally, engineered wood products specifically and focus will be focused on at the end of this lecture. So let's start. As a reminder of the last lecture, we have actually talked about the structure of the wood, and we found it to be very specific and very lattice-based, and affects and highly affects the properties in multiple directions. And we already knew that wood is an anisotropic material. Anisotropic means that the properties are not homogeneous in the same direction or in all directions. There is differences between different directions in terms of the properties of the material. And this is actually due to, the irregularity of the distribution of the internal structure of the wood that we have seen in the last lecture. And we found that wood is highly distinctive when it comes to the properties, as it has distinctive properties on the micro scale and distinctive properties on the macro scale. So everything is interrelated when it comes to wood properties. So as we said, the strongest properties for wood can actually evolve when the wood is loaded parallel to the grain direction. The grain direction is actually in this direction, right? So wood grows in the outer part or in the outer direction. So as we can see, this is the cross direction. Parallel to this direction is actually moving longitudinally all over the wood lens. So that's the thing here. The strongest properties you can find when you load the wood in this direction, in the longitudinal direction. Why? Because as we have the wood being growing in the outer direction, we can find that the wood is actually growing even in the micro scale, and we can see that those tubes that we found on the micro scale are actually growing into the depths of the material. So if we loaded the material in this direction, we are actually pressing over the cell walls of the wood, and thus we are gaining most of the resistance that is the highest resistance possible in the longitudinal direction, as the fibers in the cell wall are carrying the tension and the compression very efficiently and they are not splitting from each other. So series of tubes that are arranged in series, and those tubes are actually resisting and they are supporting each other in order to resist the load that is applied in the longitudinal direction. And that's why we have the strongest properties in the longitudinal direction. But if we are applying the load in the radial or in the tangential direction, which are the opposite or the opposing directions of the longitudinal, we can find that the wood behaves much weaker. And this is because the fibers behave like stacked straws, as if we are having stacked straws and we are applying the load, so we are splitting those straws from each other, so the material is more vulnerable and it's less resistive to the loading. So we can find that fibers behave like stacked straws and can split easily, and thus having the much weaker properties perpendicular to the grain radial or tangential direction. So this is the graph, this is the radial direction, and this is the tangential direction, and both of them are much weaker than the longitudinal direction due to the orientation of the grains. So this actually proves that the orientation of the grains directly affects the properties due to the distribution or the microstructure of the material from the inside. Any questions so far? Anything that is not clear? Perfect. So this actually takes us to a very important point, that design and failure modes actually change drastically depending on the grain direction. So if we are loading the material in the longitudinal direction, we expect a failure mode that is much different from the radial or the tangential directions. So if we are loading longitudinally, we expect the normal crack propagation, and we expect the normal brittle or the ductile behavior of ductile failures. But if we are loading from those directions, the radial and the tangential, we are expecting splitting failure. Splitting failure means that the whole thing is actually splitting and there's a crack that is propagating over the length and the radial direction of the wood itself. So different behaviors, different failure modes that we have to design using this knowledge. So it's very important to know more about the properties of the wood and the inherited knowledge behind this. So, any questions? That's great. So let's talk about testing wood and how can we quantify those failure modes and how can we quantify the mechanical properties of wood. When we do this testings, or when we do those testings, we have two techniques. The first one is a full-scale testing of wood members, and in this scale, from the name, we bring an element of wood, the real element of wood, and we apply bending, tension, or compression to see realistically how the whole wood member would behave. But sometimes this is not enough, or this is not very, let's say, practical to apply due to the huge length of the specimen that we are using. So sometimes it's much tougher for us to apply tension force because the machines available are not easy to apply when it comes to very long specimens. So the solution for it is the other way, which is the structural size testing, or which is the real testing when we have specimens, and those specimens are actually in the dog bone shape, and we apply the tension on it, or we apply the compression on it, or if we are having a smaller member, that we can apply bending on it. The difference between those testings of woods and the other testings that we have is that we can apply the same test on two different directions, whether with the direction of the grain or the other direction, which is the opposite direction to the grain. So in A here we can see a tension specimen, the dog bone shape that we can see, where tension is applied parallel to the grain, so in the same direction of the grain broth. While here in B we can see a shorter sample. This is because we are on the other side, or the other direction of the grain. So we are applying tension, and it's still in the dog shape form, but on the perpendicular on the grain direction, or on the grain broth direction. And same goes for compression testings, as we can see here in C. we can find a bit longer specimen, circular in cross-section, that is actually parallel to the grain direction, or we can apply it on the other direction where we are having a shorter height, and as we can see, it's opposing or perpendicular to the grain direction. So, same goes for the hardness too. We can apply the hardness test where we have the indentation being formed over the surface of the grains in the direction of the grain growth, or opposing or parallel to the grain direction. So this is the perpendicular, and this is the parallel to the grain direction. In both of them, we are applying the hardness test, and as we said before, we expect this to be a bit less harder than that one, because this one here, this to be a bit less harder than this one here, because it's opposing or perpendicular to the grain direction. So we expect splitting, so we expect hardness to be much lower in the perpendicular direction rather than being hard. In the bending, it's a bit hard to apply the bending in or against the direction, because bending requires a longer specimen. So we just have one orientation for bending. This is the orientation for the static bending test. As we can see, we have two supports, and we have the load that is applied in the midsection here, in the mid cross section. Then this element here will start to will start to experience flexural strain, so it will start bending, and then we can compute everything we need from the bending behavior, the flexural strengths, the bending moments, and any other measurements that we might need for this application. Any questions so far? Yes. So let's talk a bit more about the compression testings, because they are the most needed, or the most, let's say, tangible when it comes to the construction applications. As we said, we can apply compression parallel or perpendicular to the grain direction. So if we apply compression parallel to the grain direction, we experience a higher strength than the other direction. And as we can see here, 35 to 70 megapascals if we are applying the compression parallel to the direction of the grains, because the resistance is much higher, and thus we can actually have a higher strength in this direction. So the thing is, wood fibers behave like bundled hollow coulombs, as we said, tubes that are growing in the direction longitudinal, and we are applying on the same direction, which is much stronger. And the neighboring cells brace each other, so they are supporting each other against this force that we are applying. So softwoods such as pine, spruce, or fir typically reach their range of 35 to 70 megapascal when it comes to parallel compression loading. While hardwoods such as the oak or the maple or the cherry can reach up to 50 to 100 megapascal, because they have much thicker cell walls that actually resist the applied force more, and thus much stronger material. So, in some cases, such as the dense tropical hardwoods, we can actually exceed the 100 megapascal, reaching 103 megapascals, and in some conditions 100 to 110 megapascals in compression strengths that is parallel to the grain direction. So, any questions so far? Yes, please.
Did you say that the tropical hardwoods have more like cell walls?
Yes, because the cell wall is much thicker. So on the micro scale, we can see that the cell wall is the golden pullet parameter, the thickness of the cell wall, that highly affects the mechanical properties. The thicker it is, the more resistant this material will be to loading or against loading. But it actually depends on the direction that you are applying the force on. If you are pressing over the tubes itself, then this force that you are applying is distributed on larger area. So this means that the stress applied is now shorter or smaller, which means that this material can resist this force more. But if it's very thin, then the applied stress is very high, and there will be stress concentration, and thus we will have cracks that will propagate into splittings or failure. So this is the case of the directionality here, and the case of the thickness of the cell wall itself. So the species affects the compression value, and also the directionality that you are applying the force on also affects the strength of the material. Any questions? That's perfect. So, as we can expect, the other case would be the perpendicular. So compression perpendicular to the grain direction. As we can see, compressed perpendicular, or compression, when wood is compressed perpendicular to the grain, the load acts across the fibers, causing the cell walls to crush, because now we are applying the force on the other direction, on the transverse direction, where those tubes are actually stacked, so it's as if we are splitting those tubes from each other, and thus the resistance will be much lower. So this will cause the cell walls to crush and deform rather than carry the load axially and trying to resist and cooperate with the other tubes that we have on the microscale. So the result is a very low strength that can reach up to 7 megapascal, from 3 to 7 megapascals, and significant indentation from the top. So this means that this material is less harder from this direction than the longitudinal direction. So the design in this direction is usually governed by allowable deformations rather than ultimate failures, because we cannot have a fixed number for this failure point, and thus we cannot design over this. So whenever we design, we usually expect that the load will never be applied from this direction, because this is actually much lower in strength than the other, or the main direction that we are interested in. So, any questions so far? Same goes in tension. Parallel to grain direction is much stronger, can reach up to 150 megapascals, with rupture happening at the defect points, such as the holes, the knots, and more, and we'll be talking about those defects in the next slides. While the perpendicular to grains is much weaker direction, which can reach up to 9 megapascals, so it's the same thing goes for the tension properties, and this directionality highly affect the property of the material, or the mechanical property of the material. So, as for the bending test, or the bending property, as well as the shear property, as we know from the past lectures in the series of concrete and metals, bending is used to determine something called the modulus of fracture, and this is actually analogous to the modulus of elasticity. Both of them are describing the same thing, but from different directions and different loads. In the modulus of elasticity, we are applying either tension or compression, but in bending we are just applying the mid-span force that is applied to cause bending, or cause a moment that will cause bending. So wood is highly efficient when it comes to bending and bending resistance when the load is applied parallel to the grain. So if the load is applied parallel to the grain, we can find that the wood is actually very resistive, and the flexural strengths can typically range between 40 to 100 megapascal. Those numbers are much higher and much tougher than most of the known materials, specifically ceramic-based materials, for example. So we can find concrete having numbers in the same range, or in some cases lower, which means that the bending properties of the wood are much higher and much more efficient. Any questions so far? So, on the other hand, we find the shear stress. Shear stress is when we apply the force, but on two different planes. We are applying the force to rupture the material on two different directions. So wood resists vertical or perpendicular to the grain shear very well. So the shear here is an opposing property. It's a property that is much higher perpendicular to the grain shear, but much lower if we are parallel to the grain direction. So the shear strengths of the perpendicular side, or perpendicular to the grain direction, can range between 5 to 15 megapascal, because because we are trying to split the material, and the resistance of splitting in the direction where we are having the stacking is much higher than the other direction where we don't have any stacking. So in here, it's actually the opposite, because here the stacking is the thing that you are looking for that will resist this type of loading. But in the other cases, it's the tubes or the cell walls are the ones concerned with this or with these types of loading. Any questions? That's great. Yes, please.
It says it's efficient when bending is the bending mode is applied parallel to the grain. Would that not be like if this is the wood piece, it'd be like this?
Parallel to the grain growth direction is the longitudinal direction. I will show you some.
But like in this picture, would that not be perpendicular to the grain?
This is, oh, that's a very good question. If you cut the cross section and you see this load, it's the arrow that is deceiving us. This arrow could be twisted like this, right?
Okay.
So it's not the directionality of the arrow, it's how the force is distributed over the cross section itself.
Right.
So if you imagine this arrow to be
Right.
rotated 90 degrees, you will find that the whole thing will be subjected to the same force, but in the direction of the grain growth, not in the other direction.
Okay.
That's it.
Okay.
It's not a smart thing to have a 3D arrow in this presentation. So, any questions so far? That's great. So, we'll solve a very small example here, a short one, that we have done before in the metal series and actually in the PA sessions too, where we were subjected to how to calculate the modulus of fracture or the flexural stress. So, a static bending test was performed on a 50 by 50 by 760 millimeter wood sample. So the cross section is 50 millimeters by 50 millimeters, and the length of the sample is 760 millimeters, according to the standard of ASTM D143, where the span between the supports was 710 millimeters. If the maximum load applied is 3.67 kilonewtons, calculate the modulus of fracture. To calculate the modulus of fracture, it's M, which is the bending moment, multiplied by C, which is the half section height, which is in the mid-span of this cross-section that we have, divided by the I, which is actually the moment of inertia of the specimen cross-section. To calculate the I for this shape, it's BH to the power 3 divided by 12. The B is the width of the specimen cross-section, which is already given. The H is the height of the specimen cross-section from the base, and it's already given. And then you can calculate the I. To calculate the moment, we know it's the force multiplied by the distance, right? So you need to calculate the moment first, and then plug in the numbers here to calculate the I, and then you can get the flexural stress. So you have 5 minutes to solve this. So the formula to calculate the moment is actually the P multiplied by the L divided by 4, okay? So you should calculate the moment using this, plug in the numbers, calculate the moment of inertia, plug in the numbers, and then you can get the flexural stress.
Because it's half of the distance multiplied by the distance. That's why it's
So, any final answers? Yes, please.
31.2 megapascals.
Exactly. It's 31.2 or 3 megapascals. So, to solve this, we should start with the calculation of the moment. So, we start with the moment calculation, which is P, the load multiplied by the L, which is the span length given as 710, divided by 4. So, the load, or the maximum load, is 3.67 kilonewtons. That has to be transformed into newtons, so we multiply it by 1,000. Then this is actually multiplied by the span length, which is 710 millimeters, divided by 4, to get the moment of 65,142 or 651,425 Newton millimeters. Then we calculate the moment of inertia. As we said, it's the base multiplied by the height to the power of 3 divided by 12 to get this value in millimeter to the power of 4. Then we plug in all of the numbers, the moment, and the 25, which is the mid-section height, the distance between the base and the center of the cross-section. We got the whole height as 50, so the half of it is 25 millimeters, divided by the I to get 31.3 Newton per millimeter square or megapascal. Any questions so far? Yes, please.
Why the moment is multiplied by 4?
Sure. So the thing is, why PL over 4? This is the setup or the orientation of the bending test, right? And we are having a mid force with the value of P applied in the center. And we have two supports here that will have reactions to resist this force, right? Each one of them will acquire half of the load. So it will be P over 2, this is the reaction on the left, P over 2, which is the reaction on the right. So, to calculate the moment that is induced due to this force, we multiply the load by the length, right? So it's the moment around this center that we have here. And since it's the moment around this center, it's the P over 2 multiplied by this length here, which is half of the L. So it's P over 2 multiplied by L over 2, giving us PL over 4. And this is the induced moment caused by this force from each direction. So that's how we calculate the moment. A bit clearer? Any questions so far? Yes.
Will we be expected to arrive at those equations?
Oh, I can please.
Will we be expected to arrive at those equations?
No, actually, if you need to know something, you will find it in the formulations. You will not need to memorize anything, unless we tell you that you need to memorize this in the lecture. But those you should not memorize them, and you will find them in the formulation if you need them. Any questions? That's great. So, next is something that is very important and crucial for the design process of construction using timber, which is the wood production processes. Wood production processes are sequential, and they are interrelated with each other, and they are highly affected the quality of the past process or the process happening before it. So first we start with logging, and we have huge logs or huge wood pieces, barks, or the trunks of the trees. Those logs are actually sewed into the desired shape. So sewing is the first process, where we have bigger cross sections than the normals, and they could be used directly into the construction procedure. or we can cut them into smaller pieces depending on the application or depending on the aesthetics that we want to achieve. After the sewing process, we have seasoning process. Seasoning process is simply the drying process. We dry those pieces of wood that we cut to have them with lower moisture and higher stresses, because as we said in the last lecture, the more moisture we have, the lower the mechanical properties we get. So seasoning is much important. And seasoning can be achieved using two procedures. The first one is that we can throw it on the ground, under the sun, and we'll leave the sun do the whole job. The second one is to do it inside an agitated kiln or furnace. So we put this wood into a furnace, we subject it to a specific amount of heat and running air or with a good flow of air to take the moisture and to dry the whole thing. Then after seasoning, we're having the surfacing process. Surfacing process is simply, we are cutting the surface of the material to level it up, to make it leveled, so that when we use it in construction, we don't have any orientation errors or any angular errors that we do not desire. Then after the surfacing, we apply inspection. We inspect those pieces that have been cut, seasoned, and surfaced. And then we put a stamp with a grade on it. This process is called grading. And the grading procedure can be done visually or mechanically, and we'll be talking about this in the next couple of slides. And at the end, and it's an optional procedure, the preservative treatment. It's whether we apply preservatives due to pest attacks or due to moisture. If we want this material not to gain moisture very high in rate, we apply those preservative treatments if we will be storing this wood for a longer periods of time. So that's the thing here. Those are the processes that happen in the wood production. And as we said before, the grain pattern in wood is actually determined by the orientation of the fibers, which follow the growth of the animal rings that we have. So it's from the inside to the outer direction. When the rings are evenly spaced and parallel to each other in a very good uniform shape, this means that this wood is of a very high quality. And if we have a lot of problems in between those lines or in between those rings, then here comes the problems. We have defects that we have to deal with. And those defects could be in the form of knots or deformations or any changes over the surface or in the internal part of the material itself. So, any questions so far? That's good. So, when it comes to cutting wood, we have 2 or 3 strategies or techniques to cut the wood. This is the bigger log that we have here on the right, and how we plan on cutting it, and how good or bad the quality of the material produced from it will be. So, mainly we use either plain sewing or quarter sewing. Plain sewing is actually very quick and very economical because less planning is actually applied, less labor intensive, the orientation is not hard, you don't need to find a specific angle to cut the material. As you can see, we just cut it tangentially from the tip to the tip. So much faster and much economical. Got a question?
Yeah.
So, the problem here is that it might deform unnecessarily. Why? Because we are cutting on the tangential direction, which means that we are having different properties of the material on the tips than what we have at the center. So if the tips, for example, gain moisture in a very high rate and the center is not, this means that there will be deformations between those 2 poles. And this will cause warping, might cause other deformations, might cause other defects and crack propagations, a lot of problems. So the plain solid wood shrinks unevenly because it's got tangential to the cross rings, leading to internal stresses that might cause deformations and other defects or errors that we want to, that we don't want to have in our construction material. The other technique is called the quarter saw, where we cut the log in an angular orientation or with an angular orientation. So the cut here is to an angle between 60 to 90 degrees to the cross rings. This is more expensive because it's more labor intensive, more complicated, and takes more time to actually apply, and actually more wasteful because in some angles you might have some wastes on the other two directions that you might actually throw. So this is the drawback of the process, but it's much less vulnerable to deformation and shrinkage because you are cutting along the direction of growth, from the inside to the outside. So you are having a regular part with a homogeneous properties when it comes to shrinkages. So we are less prone to problems or less prone to deformations that are unneeded. And also another strength here is that when we apply nailing or when we do nailing, this material will not split easily. But the product of the plane sewing can actually split easily if we apply nailing to the surface or to the depths of the material. So, why is this actually very efficient? As we said, quarter sawn wood resists warping or any surface deformations or any depth deformations due to even shrinkage over the whole cross section, but its vertical grain makes it prone to splitting when nailed on the face. So this is the difference or the problem that we might face. Any other question? Yes, please.
Wouldn't quarter sawn, in a way, be more economic and less wasteful, considering if you have warped wood, you can't necessarily use it for all uses?
That's a very good question. What you see here is the perfect quarter saw. This is the 45 degrees cut, which in our case would be like the best of the best.
Right.
So the thing is here, usually it's not that case at all, because the process is much fast and the labor available in the site to do this process in general is not always sufficient. So they have to be much quicker. So if the angle is a bit shifted or their hands are a bit shifted from one layer to the other, we will find a lot of waste. But in the tangential, it's much easier because we are cutting one end and we are toppling, and now we have a steady ground to put or to orient the log on, and then we cut in series. So it's much easier, much more accurate when it comes to the waste. So it's efficient. Yes.
Is it cut before and then?
Exactly. Yes. That's why it's quarter, because we start with a 1/4 cut. We split it into 4 pieces or 4 parts, and then we cut each of them with a specific angle. Any questions? That's perfect. So those were the cutting techniques, and now we will be talking about the types of the board cuts, the product itself. So the produced product could be either tangential cut, or a radial cut, or an intermediate between them, a mixed or a combination cut. So let's start with the tangential cut. The tangential cut is usually accompanied or mentioned with the plane sewing, or plane sawing, I'm sorry. So the saw blade or the cutting tool intersects the gross rings at a shallow angle, which means that we are cutting in a uniform way from top to bottom, parallel to the line of the rings. So we are cutting parallel to the line of the rings to have those slices that we have seen in the past slide. And this is actually often used in plain sawn or flat sawn lumber, and more prone, as we said, to warping due to the difference in the properties between the different poles, and twisting due to differential expansion due to uneven shrinkage of the material and contraction along the groth rings. So this product is actually accompanied with the plane sewing technique, and those are the properties of it. Any questions? On the other hand, we can see the radial plane or the radial cut, this one here, where the board is sliced along the radius of the log. So cutting tool intersect the gross rings in the depths to the center at a right angle, as we can see here. So this is often used in quarter sawn or rift sawn lumber, and straighter, more stable boards with less deformations. and distinctive grain patterns, and with lower vulnerability to deformation in general, but might be prone to splitting due to nailing, as we said in the past slide. And in between, we might have the mixed or combination cut, which is usually the most favorable or the most common when it comes to cutting, especially when we are targeting a radial cut. This is the perfect radial cut, and here, this is like an intermediate cut between both angles, and it offers a compromise between the characteristics of the tangential and the radial cut. It's mostly between both of them, depending on the angle, and usually used when balance between the appearance and the stability or the strengths of resulting boards are needed. If we need a good aesthetic or a better shaped wood surface and a good strength or an efficient piece of board or piece of wood, then we tend to use the mixed or the combination cut instead. So, any questions so far? Anything that is not clear? So, both of them are interconnected with each other, the product and the technique that we cut the product with. So, in the next slide, we will be actually talking about the wood defects. The defects that we might see when we cut the piece of board or when we cut the piece of wood. That we might see in any product or any wood product at any angle. So those are the different shapes of defects that we might experience in or while cutting the wood pieces. So first, we can see the knots, and the knot is simply the remainder of a branch. If we are having a branch that is extended to a piece of wood that is on the surface of the log, and we are having this piece of wood from the surface, we can find those knots here with those circular marks, and those circular marks actually resemble the same position or location of a branch that was extending from this side. So those knots might cause stress concentration if force is applied, and might cause splitting of the wood if the force or if this piece of wood is used in load-bearing applications. So we usually try to avoid those knots as much as we can, but definitely when you go to Home Depot and try to buy any piece of wood, you will find a lot that will have those knots. This is not a bad thing because we are having an inspection procedure that we'll be talking about. If it passed from the inspection procedure, then this means that the strength is fine and the appearance is not bad. So knots is the first wood defects that we might experience. Wane is another one that we might see, and the wane is simply the bark or any soft material left from the outside or missing from the outside due to having a cut of the log from the outer surface of the cross section. So it's any soft materials that is left on the edge of the board or absence from the edge of the board. This we called a wane. Then we have the shakes and the checks. Both of them are a bit similar to each other with one difference. One of them is much deeper than the other. The shakes is a lengthwise separation in the wood that occurs between annual grains. So we might find it naturally in the wood that we are cutting. This is the shakes. As you can see, it's a bit shallow and it's not deep enough to cause a severe problem that might reject the whole piece of wood. But the checks are ruptures that are much deeper than the shakes and are caused due to uneven drying of wood. When we cut the wood and we apply the seasoning process on it, or the drying process, we expect to have even distribution of drying over the surface.